Chapter 12, Part B, Deflection of Beams and Shafts, Moment Area Theorem Method. First, moment area theorem, it just says, as we observed in previous part in chapter 12, early part in chapter 12, that d squared y over dx squared is the m over ei, area under m over ei. So in that sense, if integration or area under moment is the slope, so the derivation of a slope is equal to moment. Mhm. So if you just rewrite this equation, d theta is equal to, if you just take this dx over here, so if you just take this dx over here, and then it just says d theta is equal to m over ei dx. And it simply says if you draw the tangent at C and D, for example, and their difference, if you subtract it from each other, theta D with respect to C is equal to difference of the area between Cm over EI between C and D. And that says if you integrate d theta from C to D, it's just an integration over the m over ei, because d theta is equal to m over ei dx. So it's as if you are integrating area under m over ei dx to calculate the difference between those two tangent. So in that sense, theta d minus theta c is area under m over ei dx. So it just first moment area theorem says a theta of d with respect to c is area under m over ei between those 2 points. So that's m over ei, and that's the area under 2 points of C and D, and that's simply theta of D with respect to C. A second moment of area, it just says uh, consider 2 points of P and P prime on the deflected beam, so which they are the distance of dx from each other, and the interception of their tangents. Uh, this is the interception of their tangents, of the two tangents, lies in a vertical line passes through point C, and the tangent of those two has a difference of dt. And if you just look at a part of a circle with the angle of d theta, and just assume if our radius is x1, then dt is equal to our arc is r times d theta. And if our radius is equal to x1, dt, the length of the arc, is x1 d theta. So if dt is equal to x1 d theta, then dt is equal to x1 from the uh, first moment area theorem, which d theta is area under uh, m over ei, so that's m over ei dx times x1. So this is just a replacement of d theta from the first theorem, first moment area theorem. So what that says, and if you integrate both sides, it just says t tangent of c with respect to d is equal to integration of c to d x1 times m over ei d theta. And x1 is the distance from the centroid, or from the tangent, from the vertical line. So we'll talk about that later. So again, in of second moment area theorem, it just says a T of C E is area under C and D, area under C and D on M over EI diagram. T tangent of C with respect to D is equal to area between C and D times x1. And x1 is calculated from C. So that's a tangent of C. So it just calculated from the vertical line passes through C. That's T C with respect to D. And likewise, if you calculate the tangent of D this time with respect to C, tangent of D with respect to C, you need to go with the vertical line which passes through D. And that's the distance of x2. And x is just the centroid through that axis. X is centroid of the area through the vertical axis, passes through the, let's say, if it's t of c with respect to the goes by the first point. So it stands from first component, x bar 2 is distant from first component here. Let's put it into an example. So again, a second moment of area, it just says tangent of c with respect to d is the integration of from xc to xd x1 times mdx over ei. One can say that the tangential deviations of tc with respect to d of c with respect to d is equal to the first moment of area. First moment, do you remember that area x1 times m over ei is the first moment of area with respect to a vertical axis that passes through phi of the area under m over ei, because we are working with the area under m over ei between those 2 points. So in this example, we want to know what is the slope and deflection at end B. What is the theta and delta at the free end of this prismatic beam, cantilever beam, which is provided to us. So it happens to handle a 50 concentrated load at the free end and a bending moment of 19 kilonewton times meter. So by applying superposition, we can investigate the effect of each of the loading, then add them up together. So it seems like if we have a beam just with a moment of 90 kN plus a different plus plus the same beam with a different loading, just a concentrate at the free end by a 50 kN. So if you draw the moment for the first one, it's just a rectangle all the way through, because you can shift a concentrated moment all through the beam with the same amount, and plus a moment of uh, so at the same time we just need to know this is a length of a 3 meters, a 3 meters, and a 3 meters. So that's a, if this is 3 meters, 50 times 3 is 100, a negative 150 kilonewton times meters. Mhm. And that was the moment diagram. If we draw the moment over EI, simply divided by the EI provided with the problem statement. So and if you do so, it just says you do have your moment. You do know what your EI is in the problem statement. If you simply divided that, it just gives you 9 times 10 negative cube 1 over meter. So that's the number we have here. Mhm. So theta b with respect to A is theta b minus theta A because A is a fixed moment, theta goes 0. So theta b with respect to A is just equal to theta b, and that's area under m over EI for the first graph plus m over EI for the second graph. So if you do the math, it just gives you a theta b is equal to 4.5 10 to negative cube in terms of radian. And the other part is if you want to know what the delta maximum is. Mhm. So for delta, we do need to apply the second moment area theorem. It just says y at b is a tangent of b with respect to a, and that's nothing but area 1 times, so it's a vertical axis, it counts from b, so it's a 3 meters the total length, and the centroid to the b is 1.5, and that's a1 times 1.5 meters plus a2, which is a negative area, and again the vertical axis passes through b because that's a tangent of b with respect to a, go with the first point, so the vertical line lies in b, and the centroid to the base is 1/3, to the other part is 2 meters, so that's a2 times 2 meters. And if you do the math for yb, it just gives you yb is a negative 4.5 millimeters. Thank you. We'll work on a more example in next videos. Thank you.